Hello everyone, I am Utkarsh Shukla. I am from NIT Surathkal from India, and today I'll be presenting our paper Mechanistic Analysis of Text-to-Image Hallucination via Mode Interpolation under Classifier-Free Guidance. So let's start with the introduction. So text-to-image diffusion models like Stable Diffusion produce images that are often stunning, but they still fail in strange ways. They duplicate objects, anatomically incorrect structures, physically impossible scenes. Our work investigates the geometric reason behind these hallucinations and not just the symptoms. Specifically, we look at three things together: mode interpolation, which is a known geometric failure mode in diffusion models; classifier-free guidance, or rather we will say CFG, which is the mechanism almost every deployed text-to-image model relies on; and trajectory variance, which is a signal we use to detect when the model is geometrically unstable. To answer this properly, we ran a large-scale study consisting of 18,000 generated images across 220 distinct prompts. So let's look at the problem statement. Here's the core problem. Diffusion models hallucinate even when the output looks visually high quality, and the existing detection methods, which are clip similarity scores, object detectors, post-hoc semantic checks, they all share the same limitation. They tell you what something went wrong, but not why it went wrong. So our core research question is this: does mode interpolation, a mechanism previously studied only in unconditional models, still persist once you add text conditioning and CFG? And second, can trajectory variance act as a reliable internal hallucination detector? This is genuinely a hard problem because CFG changes the latent geometry during generation. Hallucination can be both semantic and geometric in nature, and what we really need is a detection mechanism that works independent of what the prompt actually says. So the prior work that inspired this study looked only at unconditional diffusion models, no text, no CFG. Nobody had tested whether that same geometric explanation survives once you introduce semantic conditioning through stable diffusion pipelines. This matters because CFG is universal in deployed systems today. If geometric instability changes meaningfully under CFG, that has direct consequence for how reliable these systems are in production and not just academic interest. And we also wanted detection methods that we generalize better than clip-based scoring, which, as I'll show you, turns out to be a real weakness. Let me walk you through our 5 main contributions, because each of these is something I'll come back to with evidence later in the talk. First, the CFG U-curve. Trajectory variance forms a statistically significant U-shape as a function of CFG scale. It hits a minimum exactly at CFG equals 7.5, where we measured a 0.0% hallucination rate. But pushing guidance further to CFG 15 brings a partial rebound to 1.3%. Meanwhile, clip scores just increases monotonically the entire time. That divergence is the heart of this paper. Second, per CFG discriminability at CFG equals 1, trajectory variance still achieves an AUC of 0.760, while clip collapses to 0.522, which is essentially random guessing. Our signal works exactly where clip fails. Third, a three-tier spatial taxonomy. When we look at per pixel variance heat maps instead of a single number, mode interpolation produces uniform spread across the whole image, while geometric-only failures produce sharp, localized hotspots. This distinction is invisible if you only look at the global number. Fourth, external generalization. We tested on 200 completely unseen prompts with fixed threshold, no recalibration. Trajectory variance AUC actually improved from 0.877 to 0.959. Clip AUC on the same data collapsed to 0.475. So statistically, no better than any random chance. And fifth, a dual hypothesis outcome. Mode interpolation is real, but it is CFG dependent. At the same time, 24.3% of all failures we observed are attributed to semantic assignment rather than geometry. Both explanations matter. So before applying this to real stable diffusion generation, we first validated trajectory variance on controlled toy distribution, where we know the ground truth exactly, our 1D Gaussian mixtures, 2D Gaussian grids, and a simple shape datasets. And our validation criteria was a dead zone to mode variance ratio greater than 5, and it passed in every single case. Then we built a custom DDIM pipeline for Stable Diffusion version 1.4. Stable standard pipelines don't expose the model's intermediate prediction, so our custom loop captures the model's running estimate of the final image at every denoising step without altering what actually gets generated. We compute trajectory variance across the final 15 DDIM steps, what we call the commitment video, the phase where the model is finalizing its output rather than still exploring. Higher variance in that window means the model is unstable, oscillating between different valid modes instead of committing to one. Let's look at the actual results. First, the hallucination label distribution. Out of our internal dataset, 62.3% of images are clean, 8.2% are confirmed hallucination, and importantly, 5.2% show high variance but still produced a correct output. We call these geometric only. This is exactly why we need both a variance signal and a quality check together. Variance alone would overflat perfectly fine images. Now, the central finding of this paper, the CFG U-curve. On the left, you can see mean trajectory variance against CFG scale. It drops sharply, bottoms out right around CFG 7.5 and then climbs back up towards CFG 15. On the right, hallucination rate follows that exact same U-shape, while clip score just rises monotonically the whole time and never comes back. These two signals are capturing fundamentally different things about generation quality, and the gap is what the rest of this talk is there. This next part is where we make our strongest case against relying on clip alone. If you look only at the pooled AUC alone, and which is across all CFG values, both trajectory variance and clip look similar, around 0.87 each. But that number is misleading because 95% of all hallucination in our dataset happen specifically at CFG 0 or CFG 1. So what actually matters is performance, exactly where hallucination occur, and that's the per CFG breakdown. At CFG equals 1, trajectory variance holds strong at an AUC of 0.760, and in the same setting it collapses to 0.522 clip, essentially a coin flip. This is the clearest evidence in our study that trajectory variance discriminates precisely in the regime where clip gives you no usable signal at all. Up to this point, everyone used a single number per image, global variance. Now we ask a different question, not just how much instability is there, but where is it located? We compute two spatial metrics. The spatial concentration index, or we can say SCI, tells us whether instability is spread evenly across the image or concentrated in one spot. The peak variance ratio tells us how dominant any hotspot actually is. Here's the surprising part. We expected hallucinated images to show a concentrated hotspot, like the model got confused in one specific region. The opposite happened. Full hallucinations show uniform spread. Every single pixel is equally uncertain. because the model is oscillating between two completely different global images. The sharp, localized hotspots instead show up in geometric-only failures, where the overall structure is fine but one specific region just can't resolve. This three-tier taxonomy, uniform spread, localized hotspot, and clean, is completely invisible if you look only at the global scalar. Here you can see the taxonomy made visible. Top row hallucinated images, a uniform purple haze across the whole frame. Middle row geometric only failures, a tight, bright concentrated spot. And in the bottom row, clean images, a diffuse pattern that simply follows natural object boundaries. On the right is our external validation. We took the exact threshold calibrated on our original 20 prompt and applied to them completely unchanged to 200 brand new prompts that model had never been tuned on. Trajectory variance AUC actually went up to 0.959. Clip AUC on the same external data collapsed to 0.475, statistically indistinguishable from random chance. This is our strongest evidence that trajectory variance is a genuinely deployable generalizing signal, while clip is not. To summarize, more interpolation is real, but it's strongly CFG dependent, significant at low guidance, essentially eliminated at the standard setting of CFG 7.5 that most production systems actually use. Trajectory variance is a robust hallucination detector that costs nothing extra at an inference time, and it generalizes to new prompt where clip simply does not. The spatial variance maps reveal a failure taxonomy that a single global number completely hides. For future work, we want to test this on a newer diffusion transformer based architectures like Stable Diffusion 3.5 and FLUTS, and extend the idea to video diffusion where instability might show up temporarily as flickering and explore cross attention entropy as a signal that might predict instability even earlier than trajectory variance does. Thank you everyone, and I'm happy to take any question. Thank you.